Hi, I'm Mike Byrd. Today we're going to talk about indexes and page splits. We're going to talk about good and bad page splits. And you're sure you see this slide before, but I just highly recommend that you attend your local PASS groups and also your SQL Saturdays. And of course, the virtual summit is the biggie. All are great for networking and for learning new things about SQL Server. Your feedback is important to both PASS and myself. I like to have the evaluations so I know what things are positive about my briefings as well as anything negative that may affect the quality of my briefings. So please do the session evaluations. In the past, I've been a rocket scientist, fighter pilot in the Air Force, flying F-4s and F-5s. I was a freelance tech writer for PC Magazine for about 3 years. I was an insurance company CTO for about 9 years, got a new boss, and I parted company shortly thereafter. I just didn't get along. But that got me back in the tech side of databases and SQL Server, and ever since I've been just loving to do performance tuning and teaching T-SQL. Today we're going to talk about index B-tree, page splits, both good and bad, the tested scenario results, which are really surprising to me, and conclusions. The B-tree is actually a database structure inherited from Sybase, which was the predecessor of SQL Server, and it allows rapid traversal down to individual rows. You can get down with minimal number of jumps to get to an individual row. Data is stored at the leaf level in 8K pages, both root and intermediate levels. All they do is really contain pointers to the leaf level pages, the leaf level being down at where the data is stored. Heaps and clustered index data are stored in what's called data pages, a slightly different structure than the index page. But non-clustered index data, including the include columns, are stored in the index pages also, just like in the leaf. That's a typical picture of a B-tree. It's not the typical one that you normally see. The one you normally see is very symmetrical. But in real world, it's always skewed to the left, and your bottommost boundary is a null value for your first column index column. And you can see here all the data is stored down at the leaf level, and then in the intermediate levels, if there is one, sometimes there's not, and at the root level, all they contain are pointers to get you down to the individual data at the leaf level. So what happens when you have a page that's completely full and you're trying to add another row to it? Well, when there's not enough space within the page, you got to add a new page to the index. And this is where you have good page splits and bad page splits. Usually, as you're adding data to a page, fill factor is not an issue. It's going to fill up the leaf level page, and if it won't fit there, it goes to the next leaf level page. And their fill factor is really only an issue after a rebuild, and we'll talk about that tomorrow in a session I have on fill factors. You're very welcome to attend that session also. And then, as in always the case, there is the 1% exception that Jeff Modem found, where sometimes fill factor is a issue when you're loading up leaf level pages. And that can be found at SQLServerCentral.com. Okay, good page split is mainly like, a good analogy is when your index column is an identity column, you're just adding data at the end of the table. And so when, like in this case, the third page gets full, then the fourth page you add it and it just keeps going. And what it adds is the next page in sequence. Pages are stored in extents. There's 8 pages in an extent. And so if there's another page in the extent that sequentially follows the current page, it's the one that gets added. If the extent is full, SQL Server goes and finds a new extent and then starts adding that. Notice down at the leaf level that all the pages have a double linked list. In other words, there's a previous page pointer as well as the next page pointer. And then if you have more than one page at the intermediate level, that also is a double linked list. When you have a bad page, though, is when you have data, in this case, in the second leaf level page, it wouldn't fit. So now it has to go out, and since all the data is sequential and ordered by the Azure index definition, since it wouldn't fit, it had to actually go out and find a new page out of sequence, because the next page and the third page here is a following sequence in that extent. So it usually goes to another extent and adds that page in there. So now you have an out of sequence set of pages. Notice here in this particular example, half the data is written down to the new page, half the data was retained, and the new row fits wherever it needs to fit, and it could be either the old page or the new page. Also in this example, notice that because there was no room up the intermediate level, we'd have got a second page split. So here we got 2 for 1, not necessarily good either in this case. All this is logged, and all this is additional I/O, all this data movement. So it's called a pad page splits because now you have out of sequence index pages, as well as all the additional I/Os and the login. And that possibly then you may even get bad page splits up at the intermediate and sometimes even the root level. This can also cause query performance issues because now you have additional I/Os in the index range leaks, especially as additional space from the where you have half-empty index pages, so more logical I/Os to do a particular query. We'll show an example of that a little bit later. An index rebuild will reorder data and eliminate bad page splits. Again, fill factor can be a factor in the rebuild process to mitigate bad page splits. So what was my testing here? My testing was to create an independent database with an independent tables. Excuse me, I'm checking my timer. And so I had 2 duplicate tables in this new database called test from EventureWorks 2017. Big is because Jonathan Hess has a script to expand sales order detail from roughly 300,000 rows to just under 5 million rows. So for the first one, I added almost 50,000 rows at the end of the clustered index in sequence, and so that's good page splits. For the second one, I added the same number of rows, and that's each row roughly in the middle of each index or each page within the clustered index. So with that, I recorded pages added, CPU, I/O cost, bad page split, split count, and so forth. Let's look at just briefly at the, okay, so there are 500,000 rows, 49,000 for that. If I divide 500,000 rows by the number of pages, I get about 98.4 rows per page. So let's just assume it's 98. So I went out and put in a temp table the data I wanted to insert in the middle of the page. Notice I used offset of 49, and then also used the modulo of 98, and that ended up with 49,517. Added a constraint, deleted those rows from the table, rebuilt the table, got some numbers on the table, stopped my extended event that gets me bad page splits, excuse me, and then I reinserted it in numbers here. Numbers I show in my slides. Wow, look at the difference in page counts. With the end of row inserts, we have page count went from 48 to 49, but then it went on the mid-page inserts went from 48,000 to almost 94,000 pages. We can look at the difference in logical reads. Also, we had 11,698 and jumped to 428,413. That's a 36 times increase in logical I/Os. And you can see CPU also jumped a bunch too, and that's about a 600% or 6 times increase in the CPU utilization. And the numbers bear out per row. Your CPU cost for a row insert was about 0.005 milliseconds, and it was about 0.03 milliseconds for the page splits. Look at that. So there's your 600 again and your 3600 again. So numbers don't lie, and don't take these as gospel numbers, but they do show the trend. Also look at 2 very simplistic queries, one on the test 1, which was the end of row inserts, and test 2 was the mid-page inserts, and you can see difference in CPU, 735 to 874, and then number of logical reads. Then the logical reads are greater for the mid-row because of all the bad pages that were inserted that have to be read also. So what does this mean? Well, bad page splits, we already know, increase I/O and CPU time. Now you have some firm numbers to look at. Bad page splits will also affect subsequent query performance into your indexes we built, mainly because of the page splits and not necessarily full pages that result from the page splits. Don't use these numbers, or these numbers should only be used for trend and don't necessarily apply to other scenarios, but you can try other scenarios and see if you get similar type results. My big question now is, what is the trade-off for lowering fill factor to reduce page splits versus the growth in index size because of the reduced fill factor? Big question, not going to be answered here. Thank you very much for your time and pleasure. It was a pleasure to chat with you, and I hope to talk to you all later. Bye.